So with that, since you already kind of gave half of the introduction for me, it takes me about 5 seconds. My name is Brandon Lewis. I'm standing in for Chris tonight. He has a conflict, so this is about 15 seconds. You're going to hear me tonight. Of course, we have Seth Johnson talking to us about practical auth. I'm going to take a quick second to just thank Manifest Solutions for providing a dinner tonight. If you're thirsty or want water, we do have little bottles of water in the little mini fridge in the back, so feel free to help yourself. That's it for me. All right, let Seth come up here and do his thing.
Okay.
And learn a little something.
Oh man, now everyone expects to learn something. I feel all this pressure. Okay. All right, so welcome to Practical Auth for Developers. So over the next hour, I'm going to take you on a guided tour of 10 different authentication and authorization techniques that you might want to know about. At the conclusion of the hour, assuming you all stay awake, you'll be able to leave this room having a basic understanding of how those things work in relation to each other. So our journey begins with a confession. So a few years ago, I made a huge rookie mistake. Right? I had a web app, writing a feature. I needed some JavaScript to call out the API in the server. And the server needed to know who was making that call. And I didn't know how to tell it who was making the call. So I Googled, how do I authenticate an API call? And that's kind of a mess. There's all this stuff about bearer tokens and nonces, federated identity systems. There were Reddit fights over the right cryptographic function to use when you're hashing as a request. There were 2 different versions of this thing called OAuth that worked entirely differently. There's this thing called the JSON Web Tokens that some people said were awesome and other people said were a scourge on the internet. So it was totally confusing. I was in a hurry. I went to Stack Overflow, cobbled some code together, and spoiler alert, I shipped the defect, right? So the goal today is to give you kind of the coherent baseline understanding that I needed back then. I'm going to break down all that complex terminology and compare and contrast those techniques so that when you need to choose an auth strategy, you can make an educated decision and not a rookie mistake. So I want to be clear about what the session is not, right? I am not a security expert. This is not an advanced security session. If you already know the difference between OAuth 1 and 2, how to sign a request using HMAC, or how to use JSON Web Tokens to eliminate server-side sessions, you're going to be bored for the next hour, right? My target audience is people who don't know those things, or that those are things that you can learn about in the first place. Also, I'm not going to show you how to implement these things. There's stuff I'm going to talk about that I've never written any code for. I've never written any OAuth code myself. I couldn't tell you what step 1 is. But what I have done is Google the crap out of OAuth. Or more typically, I Google the crap of how OAuth compares to anything else that you can do. And that's what this is, right? This is all that research packaged up, distilled into what I hope is an easy to understand explanation of how these things work together and compare to each other. This is what we're going to cover today. Quite a lot to go through. But before we get to that fun list, I want to define 3 concepts that you need to keep in mind when you're securing a system. Let's say we have this website, and a request comes in for some URL, like foo42. So the identity is the person or entity that's making that request. Authentication is how we associate the identity to the request. Right? It's how we know that it really is our friendly user Alice over here. And authorization is whatever rules dictate if the identity can do the request. Whatever business rules tell us if Alice can access 42. So when we're talking about authentication, it's generally considered a bad idea to just blindly trust the client when they tell you who they are, right? We need some reliable way of verifying their identity so we know it really is Alice and not someone pretending to be Alice. And there are three main types of authentication factors that we can use. Something you know, something you have, and something you are. So passwords, great example of something you know. We know Alice's password, she knows her password. If we both agree, we assume that it really is Alice. So key cards and authenticator apps are an example of something you have, right? These are installed for or given to specific people. They're registered, so that's a factor of authentication. And then biometrics are an example of something you are, right? Unique fingerprint, retinal scan, whatever. So I'm going to talk about the first two factors today. I'm not going to cover biometrics. But once you understand how the first things work, you'll have what you need to understand biometrics if you want to research that further. All right, so the most common auth factor on the internet is a password, right? We've all used them before. This is not, new. But I want to start here because the everyday run-of-the-mill password implementation demonstrates two important concepts that kind of underlie everything else we're going to talk about. So here's our lovely user Alice logging into our website. And even though the password is masked on the screen, right, it's still included in a forum post as plain text. So it goes out over the wire as plain text. So if Alice is sitting at her local coffee shop on their free Wi-Fi, and her credentials could be visible to anyone else who's eavesdropping on that same Wi-Fi connection, or really anywhere else on the internet between her and the server. But if you use TLS, then the network connection is encrypted. So all that traffic over the wire is encrypted, and anyone eavesdropping on that connection will not be able to steal her credentials kind of while they're in transit. So TLS provides security and in transit because the sensitive information is secured over the wire. Now, the key thing about encryption is that it's reversible. And that's kind of the whole point, right? The sensitive information has to be turned into gibberish when it leaves the browser, travel across the internet as gibberish, and the server has to be able to turn it back into that plain text to do something with it. So that idea of reversible encryption was the first thing that I wanted to kind of talk about with passwords. The second concept comes up when we talk about what happens when we validate that login request on the server. The simplest thing that we could possibly do is store our passwords in plain text in our database. If we did that, it'd be really easy to log someone in, right? We just query for a user for a plain text match on username and password, and that'd be it. But of course, if we're doing that, then we're not providing security at rest. It's anyone that gets access to that database file has all our credentials, very easy. It's considered very bad. So we could also do encryption here, right? We could encrypt the passwords in the database and store the encrypted version. And if we did that, then the login verification will be just as easy because we would just encrypt whatever the user sent us, then search for that. But there are two reasons not to do this. The first is that our website really has no legitimate need to know Alice's password. Right? We need some way of validating that she entered the correct password, but we don't need to know what the characters actually are. So we don't really need that reverse ability of the encryption. Secondly, if an attacker can get access to that database and they get the encryption keys, then they can very easily decrypt all the passwords. It's essentially like having them as plain text. Not as easy, still possible, and the payoff is still really huge for an attacker.
So how the encrypted key will be accessible to the person? Must be part of the database, or only DBAs would know that, right?
Correct. Yeah. I mean, so if you encrypt it, then yes, that's sort of out of scope of the talk, right? The idea is that hopefully you could protect or keep them secure. My point is, if they're not, if they get cracked, then it's essentially all the passwords there in clear text. So yeah, I may have this might not be easy. It could be really, really hard to get that, but it's still possible, right?
It's been done.
Yeah.
Under the sun, it's been done, yeah?
Yeah. So to kind of address those issues, we can use hashing functions. That's the second thing that I wanted to demonstrate with a password-based authentication. So hash functions are similar to encryption, And in both cases, you pass some sensitive string into a mathematical function, and you get some gibberish as output. The key difference is that hashing is a one-way operation, while encryption is reversible, right? So if we store the hash in the database, then the hash is not reversible. Then even if a hacker gets access to the database, they can't easily reverse that into the actual password they would need elsewhere. The other thing about hashing functions is that they convert every unique input to a single deterministic unique output. So no two passwords put to the same hashing function will generate the same result. So we can store the hash value in the database, not the password itself. When someone goes to log in, we just rehash the value that they sent us in their password, and then we search for the result, right? If it matches what's in the database, we know the user entered the right password because only that string will convert that, will hash that same value.
So when the user submits, that goes as a hash to password?
Yeah, so the user submits in plain text,
Plain
right? Server gets it. So user submits in plain text. Server gets it. Server says, I'm going to hash what they entered here. That turns into this. I'm going to query for this. That's what's in our database, right?
But what is the man in the middle is between the,
Yeah, I'll talk about man-in-the-middle attacks in a minute.
yeah, because you earlier talked about between the client and the server.
Mhm.
Now-
So correct. Yeah, I'll cover that in a second. Yeah, we'll talk. So obviously, if you're sending it over, if you're sending this password in plain text, you want to make sure that that whole submission is TLS protected. Well, sure. So, but the key thing here is that our website has no easy way to reverse this into Alice's actual password.
Now, what if like a user changes their password? Will they get a new complete hash as well?
Yeah, so yeah, if the user changes their password, then you'd want to rehash or restore the database, correct? So I'm oversimplifying a little bit for the purposes of the talk. There are things about salting your hashes. There's rainbow tables, a bunch of stuff that you want to search into if you want to know more about this. My point was just to demonstrate the idea of using a hash function to convert a sensitive value into a less sensitive value. Right? Yeah, again, so attacker gets the access to the database. He can't reverse those things, at least not at scale. So that covers how we might authenticate the form post itself, right? The login form. But once Alice logs in and she starts making more requests, how do we know that these requests are coming from Alice? There are primarily three ways of doing that. So for an interactive website, the most common approach is for the server to keep track of sessions on its side and use a session cookie that gets sent to the browser, indicate kind of a pointer to session memory, right? So if you go this route, it's really super easy because your web framework does all the work. Right? You get a cookie, you send the cookie back to the browser automatically, server just knows who you are. It doesn't really work for API calls or other things, right? But it's easy for a web app. You can also send credentials through HTTP headers, which we'll come back to in a minute. The third option is to use X509 client certificates. These are basically like reverse TLS. And I don't have any hands-on experience here, so if you've done this before, don't yell at me if I oversimplify it. But basically the reverse TLS. So when you use TLS, you install a certificate on the server. And that tells the browser the server is who it claims to be. That's how your browser knows it's talking to your bank and not someone pretending to be your bank. Client certs are installed on the browser and they prove identity to the server, right? So it's a really nice option if you're building things like an internal system where you can actually get users to install them and you can manage the certificates. Not super easy, does not scale to the public internet, so I'm not going to talk about them much, but they are an option for authentication if you're building like a private network or something where you have control over your user base. So passwords and session cookies work great when there's a user sitting at the other end of an interactive session. But what about computer-to-computer communication? Like when one app needs to call an API on a different app. Right? We can't redirect to a login screen because there's no one there to actually log in. So in this situation, we can use something called basic authentication. This is an internet standard and describes how to send credentials over the internet as an HTTP header. So the name of the header is authorization, which I always kind of threw me for a loop. It's kind of misleading. This header can be used in lots of different ways. Some of them are authorization, some are authentication. So it's kind of a weirdly named header. Just know that it can work for both of our cases. And here's how it works. To follow the basic auth standard, the first part of the header is the scheme. It kind of says, this is what it tells you how to interpret what comes next. For basic auth, what comes next is a base 64 encoded credential pair. I'll tell you how it works. So the client still needs to know the username and password, right? We're still talking about something you know as an authentication factor. When it's ready to make an authenticated request, it combines the username and password with a colon between them, and then base 64 encodes that result. That generates some kind of gibberish string, which is then passed as the header value. Now, obviously, I truncated this for aesthetic purposes. The real header is the whole value is sent. The key thing to remember is that encoding is not encryption, and encoding is not hashing. So unlike hashing we just talked about, this string is 100% reversible back to this pair, this string right here. No special key required. So encoding is about making the string easier to send. It has nothing to do with securing it. So therefore, right, if you're doing this, you always want to make sure you're using TLS on the connections to keep those credentials secure on the wire. So basic auth supports some automated scenarios, but still requires access to a password. And there's one big issue with using passwords for like computer-to-computer authentication. Namely, that passwords are the user's primary credential, right? They're the key to the entire kingdom. Let's say that we have this URL, right? We have our API endpoint here, and it returns some basic, not very sensitive information. Maybe we still want to require authentication because we want to do rate limiting or we want to monetize or something. But the data being returned is not terribly sensitive. It'd be really bad practice to require the primary user credential to access this relatively unsensitive information, right? Because the value of protecting that data is far less than the risk of losing the primary credential. So instead of using the full account passwords for like your API calls, you can use API keys as a kind of limited privilege password. So let's say that our app has integrations with multiple third-party applications. So instead of using her primary account password for each of those, we could create separate credentials for each of those integrations. So if someone hacks one of them, that's all they get access to. They can't then leverage hacking this integration to hack this integration. And neither of those keys is actually used to log into Alice's account, right? They're used for these single purposes. They're not used to log in. There are two ways to do this. One is to pass the API key as an HTTP header. So when we do this, it's called a bearer token. And bearer token is like cash. Anyone who has it can use it. There's no restriction built into it. When you do this, the API key is passed as plain text, so the server can then take it and then use it for authentication. Now, if you care about internet standards or interoperability, then you might want to look at using the authorization header with the bearer scheme, kind of designed for this purpose. But lots of people will also use like custom HTTP headers. And that's just fine if you're dealing with a limited number of clients or you're working internally or whatever. Now, there's no specific format for an API key, like there's not a standard, but they need to be pulled from a pool of values that's large enough that brute force attacking doesn't make a lot of sense. So GUIDs are a good place to start.
So this is only for first time authentication or regular chatting between computers?
So this is basically using an API key instead of a password to authenticate. So you're saying you would build this as a separate table or whatever, where you would link, and I'll talk about this in a second, link your keys to your people. So that you're essentially, you're assigning them multiple passwords, but these other passwords are only used for your API calls. They're not used to log in.
So it's just like the thing where you say, remember me next time.
I think remember me is more like a cookie, something similar. This would be more like if you went into, I go into, I use a shopping app, right? Where like a shopping list app, and I have my Google Authenticator hooked up with an API key. And then I create, or my GitHub, right? I create a new API key for GitHub.
Okay, yeah.
Things like that, so that you have these single purpose.
So like, when I connect my IDE to GitHub and I.
Yeah, those that.
Okay.
Yeah, that can use an API key. They may also be using OAuth or something else. But yeah, the idea there is you're using a credential that's not your main password. So if it gets lost, that's all you've lost. You can easily revoke it and you're good. They can't log in as you, right? They can't impersonate you with it. So you could pass those API keys as query string parameters as well, right? It's just a value that we're passing around. But if you do that, they're probably going to end up in your log files. And these are basically like passwords, and you wouldn't normally want to pass within your log file. So generally, it's recommended to pass these things as a header as a easy way to keep it out of your log. So the other way of using API keys does not require sending them over the wire. This technique is called signing the request, and it uses the API key plus a hash function to create a cryptographic signature for the request. That sounds really mathy and complex, but it's not. Here's how it works. The client still has to know that secret value. In this case, it's an API key, right? That's still knowledge of that secret value is still the basis of authentication. When the client is ready to send an authenticated request, it prepares its message, like a URL with parameters. It then concatenates that string with the client or the user's API key. So this creates a string that's unique to our user Alice, because anyone else accessing that same URL will get a unique string by virtue of having their own unique API key. The client then runs that string through a hashing function, which results in a unique signature for the request. And again, that is unique because a hash function always returns a unique output for a unique input. No other approach will generate this exact string unless it's this URL plus that API key. So the client will then submit the request to the server, right? It makes its normal request with its full parameters or whatever, and it passes the signature as a header. Now the API key itself is not sent over the wire. It's used to calculate that signature. The API key itself is never transmitted, and because the hashed value cannot be easily reversed, if an attacker were to capture that, they cannot easily reverse it back into the API key. So signing requests also protects them from man-in-the-middle attacks. Let's say that this bad guy here has managed to infiltrate some network segment between Alice and our server. And he wants to change something about that request while it's in transit. Right? Maybe he wants to change one of the parameters so that what the server receives is not what the user originally sent. Real world example is Alice sending money to a friend. Bad guy wants to put his account number in place of the friend's account number so that he gets the money. But signing requests means that won't work. Because when the server receives the request, right, it's going to look up Alice's API key. It's going to recompute that signature. It's going to take the URL that it got. It's going to add Alice's actual key to generate a signature. And if those things don't match, then it knows that something was altered in transit and it can reject the request. So anyone in the middle trying to manipulate that message will end up generating a different signature. That's how the server knows something changed in transit.
So how do they compare?
Sorry?
How do they compare those values?
Oh, so the server, right? You get the server, the request has the URL, whatever that URL is, and the original signature, right? So the client generated. The client generated that signature that's passed through. So the server, who knows the same private key and the same hashing function, just recomputes the hash.
So they have map of the key versus the user.
Mm-hmm. That's how I'm going to get there. You're asking me, how does it know what key to use?
Right.
You're ahead of me every single time. Just bear with me. So yes. Okay. All right. So yeah, they match. The server knows that it received what Alice sent and nothing was modified in transit. Now I glossed over one important detail, like you were just holding me accountable for, but the whole process depends on the server using Alice's key to recompute that signature. But there's nothing in this request that tells us which key to use. Right? Nothing tells us we should use Alice's key versus someone else. So how do we know what key to use? So when you're using API keys to sign requests, your request needs to indicate both the identity and a signature. Very similar to basic Auth, which has the same kind of requirement. So this ID tells us which user's API key we're supposed to use when we recalculate that signature. So you could use some primary key like your user database ID or your email address. That's worked fine, unless you want to create multiple API keys for each user. Since API keys are often used as usage-specific passwords, users might have many API keys. And if I have many API keys, then the server, if I'm only passing my user ID up here, the server has to try each of these in sequence until one of them validates. That can be a lot of wasted, effort. So generally, API keys are issued as a key pair containing a public portion and a private portion. So the public portion is sent in the header as plain text. Right? It's not sensitive. It's unique in the database. It just tells the server how to find the private key to use to validate the signature. So typically you can issue these just as two different strings. The one you pass through in plain text, the one you keep private and secret. So this idea of concatenating a string with a private key, running the result through a hash function, and then comparing those signatures is the foundation about everything else that we're going to talk about. And it's so important that it has its own acronym. So the signature is an authentication code. It's created using a hashing function, and it's used to validate a message. So it's called a hash-based message authentication code, which is often abbreviated as HMAC. So if you see this term, all it's talking about is taking a string, adding a private key, hashing it, sending the result over the wire, and then recalculating it on the other side.
That should be done by the browser or by your app. Or is it your postman? The postman has to do that. Who would do that?
Who would do the
Hash.
the hashing? So typically the hashing is going to be done by the client and the application server. So it's likely it's going to be something in your web framework somewhere.
Okay.
Again, there's lots of ways to implement this. I know what works, what I've done in my app that I've worked on for 15 years. That's about my limited. So I can tell you how it works in theory.
So if you're using Postman, so the public APIs, Postman would do like hashing.
I don't know if Postman has a way to do hashing. Typically, when I've used Postman, I calculated like, I guess you could. I mean, you could have it set up to do it this way if you were you would just need to have a step to calculate and do the hash. So you probably could. The Postman things that I've done haven't been a two-step process, one step to get a token and the token you pass along. So it's a different approach.
The key size have to be exactly the same hash.
Yes,
How would that make sure that they're the same hash? Could be using maybe a different algorithm, right?
yes. And I'm gonna come back to that in a little bit. So that's the trade-off there. When we talk about OAuth, we'll come back to that. But yes, you have to do it exactly the same way. So if you ever looked at like on AWS, they have the instructions for how to like prepare a key for doing like your OAuth stuff. It's this huge, massive list because you have to be very specific about what parameters you use, what headers do you include, do you sort them in some way? How about casings? Any difference will throw it off. And if you say, I'm just going to grab the whole request, I'm going to hash that. There's a header in there, and someone's network device adds a different header in the middle, right? It could break it. So the complexity of doing this is that you have to make very clear, sure that both parties are doing the same thing. The trade-off is that you get higher security. So if you don't want to do that, you just want to pass a token around like a bearer token, it's a lot easier, but it's less secure because you give up some of the man-in-the-middle protection.
And the abstraction on this is when you use a SDK,
Mhm.
it usually automatically does this, right? So the example I've been working with recently is Stripe
Mhm.
payments, and inside of their SDK, it
They do
does
this, yeah.
all that stuff. So it does all the heavy lifting.
Mhm.
So you just don't have to worry.
Yeah. Again, when I talk about OAuth, it's the same thing, right? I mean, it's pretty complex, but you get an SDK that does a lot of it for you. Yeah, good question. All right, so where was I? All right, so there's one key thing to remember. In order to use API keys, the client has to be able to securely store that key. That means the client has to, put it somewhere between requests. So if we're doing like server-to-server communication, it's pretty easy, right? We just generate some key for Alice, and then some developer on the other side downloads that key from our website, throws it in the config file, and that client app can then use that key to make requests, right? Very easy. But what if the client isn't another server? It's one of these newfangled JavaScript React front ends, right? Let's say Alice drops by her local library on a Sunday to use your application, and you're using a React app. There's no way to preload her API key onto that server in advance, or that browser in advance, right? So we could have Alice log in, and then we could send the key back after we authenticate her. But there isn't any way for her browser to securely store that key. That's because JavaScript is an insecure environment, right? Its crypto functions can be monkey patched with compromised versions. Local storage can be attacked through cross-site scripting, et cetera, et cetera. So the rule of thumb is that anything you put, any data you expose to JavaScript is exposed to inspection by a malicious script. So if we're working with a JS front end, we can't expose the key to the client without exposing the key to the attacker, which then allows him to log in or to impersonate her. So one solution to that problem is JSON Web Tokens, pronounced JOT. I often call them JOT tokens, which is the same redundancy as ATM machine. So if that kind of thing bothers you, I apologize in advance. I can't stop it when my brain works. But anyway, in a JOT scenario, the server has a system level private key that is not shared with any clients and is not sent out over the wire. Right? It's a system level key. Now, a user is still required to authenticate in the beginning. Web tokens do not replace authentication. They just give us a way to record that authentication has happened. So after the user is authenticated, the server constructs a JSON document of claims. And claims are just pieces of data, just name value pairs, right? Such as the user here is Alex. So the server then signs those claims, like we already talked about, but this time it's signing the claims with its private key, not a user-specific key. And that creates a signature, right? Here's the claims, there's the key or the signature. It then creates a token. Token contains the claims in text and the signature, right? The server's key, not part of the token, the claims are. That token gets sent back to the browser. And then the browser resubmits that token with all subsequent requests. The server receives the request, same process as before. It takes out the claims, it recomputes the signature with its private key, and it compares those two signatures together. If they match, it knows the claims document was originally signed by its own key and was not modified in transit, so it can trust the values.
Inside of the claims, is it usually information about the role of the user? Is there anything else, like inside my mind, that's my mental map, it's just roles?
You guys are really good at getting like 1 or 2 slides ahead. Yeah, I'll talk about that in a second. It can be anything you want, really. So let me get there. So the similarity to sessions is that with a server-side session, the cookie contains an ID, there's some server memory, but here it's self-contained claims, right? There's no server resources required. All the data you need can be in the claims. So to your point, we could use this for authentication only by just returning Alice's username or whatever. But we could also include things that we need for authorization, such as, is she an administrator or not? Or even, what kind of very granular permissions does she have, right? You could include those things. And the nice thing is, you don't need to hit the server to get that information. So if you have a high volume web app, this can reduce the amount of database access that you're doing during your authorization and authentication steps. Now, there's one very important trade-off with JSON Web Tokens. You can either store sensitive information in the claims, or the claims can be visible to your JavaScript code, but you can't have both. If you expose your claims to JavaScript, you're exposing them to anyone else's script, so you can't put sensitive information in there. So if your JS app can read the actual claim data, so can the bad guys. Now, again, you can't change it, but they can read it. So in practice, there's 2 places to store these tokens. You can store them in local storage or in HTTP-only secure cookie. If you put a token in local storage, then your JavaScript code can access the full token, right? It can parse it, it can see it, so you can't include sensitive information. You wouldn't want to put Alice's social security number in there. If you store the token in the HTTP-only secure cookie, then the claims are hidden from JavaScript. They're sent back to the server with each request, but JavaScript code cannot access them, which means that you could include sensitive data. You just won't be able to read it with your own JS code if you need to, right? So you have a choice to make. So I used a JS client as an example, but web tokens, can be used for server-to-server calls. It can also be used for single sign-on, right? Like, so if say you have 2 web applications, they both have access to the same private key, right? Alice could log into server 1, she gets a token, sends that token to server 2, which can still authenticate her, right? So if she's signed on in one place, you can go access 2 places, what's called single sign-on. Now, one word about caution about JWT tokens is that their stateless nature is a double-edged sword. That token is valid for as long as the server can validate it, right? So what if Alice's access level changes, right? Maybe she was an administrator, and then she went and won the lottery, quits her job, right? I'm out of here. If she continues passing that token to server 2, and that token still validates, remember, it's not in the database, it's just validating the signature, she'll be able to keep having access. So typically, you're going to want to include some kind of expiry date, some kind of expiration when you do this, some kind of revocation approach. In this case, if you did it like this, the server would first validate the signature, make sure the claims are all valid. And it would then examine the expiration date, and if needed, kick the user back to re-authenticate. A more complex approach is to use what's called a refresh token. So when you sign in, you can be given both a refresh token and an access token. The access token is meant to be very, very short-lived. So it's self-contained, no database access, but only lives for a short period. When it expires, you would then use the refresh token to get a new access token, and that would hit the server to make sure that your API key is still valid, hasn't been revoked. So moral of the story is have some way to revoke your keys. And if you go back to the, if you go back to in the beginning, my rookie mistake was that I created a way to have a token that never expired, right? So you log in once and you're logged in forever. So you definitely want to make sure you have some way to expire these type of things.
What is your definition of short-lived? Is it sort of matching to a session? So in some applications, you could have a session for an hour or a week. It just depends on the app.
That's, the classic computer science answer of it depends, right? It depends on your use case. Depends on the data, how often will it change, and what's the risk or the penalty of having it be stale, right? So if you're highly, highly secure, then maybe you want a very short token. If you're like, I just want you to re-log in once a day or once a week, it just depends on how much you care that Alice can log in after she quit her job, right? So it really is up to your business case. All right, so we've covered a lot so far. Passwords, basic auth, client search, API keys, all use user-owned credentials. JSON Web Tokens are a claims-based system that uses a system-owned credential to sign a request. So we're going to talk about SAML next, which is similar to JSON Web Tokens. It's often used for single sign-on, like we just talked about. And the elevator pitch for SAML is that it's like an enterprise-grade XML version of JSON Web Tokens. And I know that XML is like, outdated and nasty. Other cool kids are using JSON. But there are mature libraries and SDKs that kind of hide away all that nasty crap. And it's worth knowing about because this is still very widely used in single sign-on scenarios, especially in the enterprise. Because web tokens don't cover some of the advanced scenarios that SAML does. It can get really, really complex. So there are three parties in a SAML scenario. There's the user who's trying to do something, it's Alice. There's the service provider, which is the website that Alice wants to log in or do something with. The third party is the identity provider. That's who's going to authenticate Alice. Like MS365 or Google or whatever system that you're using. So Alice starts by going to the service provider. She does not have authenticated session. So she's sent over to the identity provider where she logs in. And she can log in doing whatever they want her to do, whatever their protocols they have. They will then sign a set of claims stating her identity and send her back over to the service provider, who then validates the claims and says, cool, we know now this is Alice. Now the key though is that both providers have to agree on the same value to identify a user, right? If Microsoft says Alice's email is alice@outlook.com, the service provider has to be able to map that email address to someone in their system. So if you're doing this for SSO, you got to pick some value that's going to either always be the same or will be kept in sync as it changes. So email is generally, or can be a bad example because people may change their email addresses and it can be a kind of a pain to sync those up. One really nice case for SAML is outsourcing multi-factor authentication. Some of my clients require MFA for security and regulatory reasons, but I don't want to be building authentication systems, right? They're expensive, they're painful. I don't want to mess with it. So with SAML, we can push all that off to a third party. That third party can implement whatever protocols they want, whatever they need to for the user. And all my app has to do is match up that credential to someone in our system. All right, let's talk about OAuth. Also a three-party scenario. Let's assume we have a website called Totally Trustworthy Photos. And they compete with Shutterfly. They let you make holiday greeting cards with your pictures. TTF, as I'll call them for short, is really user-friendly. They will take your Facebook photos from Facebook so you don't have to upload them directly to their app, right? Pretty standard use case. The naive way to do it would be for Alice to give her Facebook credential to that web app, who would then access her Facebook account using her credentials. That's kind of dumb. And if you did that, then Totally Trustworthy Photos would be making an authenticated request to Facebook. Facebook had no way to tell that it wasn't actually Alice on the other end of that request. But what if TTF isn't trustworthy, right? They don't have her primary account credential. They can do all kinds of bad things with it. That's why we don't want third parties making authenticated requests on behalf of our users. So OAuth addresses this by providing a system for delegating authorization to a third party. Basically, Alice will authenticate to Facebook where her data is stored. She tells them, yep, I want you to show my photos to TTF, but nothing else. This is where you see that screen you've all seen where you go somewhere, hey, this app wants to do X, Y, or Z. And you say, yep, allow it. That's OAuth. So Alice logs the TTF, which is now making an authorized request to Facebook. The key is that Facebook knows that the request is coming from this web app. It knows the data is owned by Alice, and it knows what level of access she's delegated, right? So Alice makes her fancy greeting cards, keeps her Facebook data safe, win-win. There are two different versions of OAuth. They solve the same problem, but they use two different approaches. OAuth 1 uses signed requests, which is very secure. The server and the client, they know who they're talking to. There's no man-in-the-middle issues. But that signing process is complex, like you were talking about. Both parties have to do this, that signing the exact same way. That can be difficult to get right. 1.0 is also really only designed for web clients. That whole web redirect doesn't really work for non-web use cases. OAuth 2 was designed to simplify things. So it uses bearer tokens, no signing, which is much simpler. It also provides support for non-web or enterprise flows. When I first wrote this talk, the first version of this, there was still a lot of debate over which was the right or the best one. I think OAuth 2 has largely won out, especially in public-facing things, probably because of the ease of use. Just keep in mind that if you're working on a really secure system, the additional security of signing requests might be worth it.
If I were a bank, would I use OAuth too?
Depends, for authentication or authorization.
Authentication.
No, man, you guys are really good at getting one step ahead of me. I love it. I paid you all, you're all plans. So there's the key distinction I want to make. I want to go through this process in a little more detail before I get to what you're getting at. So Alice goes to Totally Trustworthy Photos to make a greeting card. They don't recognize her, so they send a 302 redirect to Facebook's OAuth endpoint. She redirects, and that redirect includes parameters to say, hey, this is coming from TTF, we want this scope, and when you're done, send her back to our site. So Alice agrees, yep, I'm cool, I want to give access. And then she's then redirected back to Totally Trustworthy, with an access token. TTF takes that access token and it lets her log in and then uses that token to call Facebook. When they call Facebook, that's an authenticated and authorized request. It's authenticated as TTF, authorized by Alice. The question is about Alice's interaction with TTF. They have an access token for her photos, but is Alice authenticated to totally trustworthy photos? Can they be sure it's Alice on the other end of the call? And the answer is no, because OAuth is not an authentication protocol, and it should not be used as one. It's about allowing delegated access to data. It does not allow anyone to log into her account. All right, okay, but and the reason for that is that did I skip something? No, good. Okay, sorry. I had it myself. And the reason that you can't, that authentication is all about associating the identity to the request. But the OAuth access token doesn't tell the client anything about identity. The token is something that the client can use to get data, but the OAuth token itself is a black box. Clients cannot extract data from it. And if the token can't tell us anything about identity, it can't be used for authentication. All right, you say, but what if the token allowed us to call an API that gave us identity information, right? What if we could call a Facebook API with that token and it gave us back Alice's email address, right? So that happens. TTF checks the database. They say, yep, we have Alice in our database. Let's go ahead and log her in, right? Is Alice authenticated to TTF in that scenario? And again, the answer is no, because access tokens don't support audience restriction. And before I explain that so far, nothing's wrong. Right? It really is Alice accessing her own data. Everything here is kosher. But there's no guarantee that it was Alice that authorized that token. For example, let's say Alice has already gone through that flow, right? She has her access token. She's gone over to Totes Trustee. She's given that token, but they're not trustworthy, right? They go over, they take her token, and they call a site called super secret stuff. Doesn't matter what they have, but it's sensitive. Big deal. So super secret stuff says, hey, I don't know who you are. Let's start the whole OAuth flow. But then the hacker says, yeah, here's Alice's token. Let's just go ahead and use that one. So super secret stuff says, cool, I have a token. I'm going to call Facebook. Ooh, look, I have Alice's email address. If Alice has an account here with that same email, and they let her log in with it, then they've essentially allowed totally trustworthy photos to get access to her data at the other site. So neither of those two sites has any more access to her Facebook data than she authorized. Her Facebook data is secure. The problem is that a token granted here, Totes Trustworthy, was allowed to be used on a different site. And if that other site uses that token as authentication, it's allowed someone to come in who's not been proven to be Alice. This happens because OAuth access tokens do not have audience restriction. Right? It's a problem of bearer tokens in general. Super secret stuff had no way to know the token they were given wasn't really for them. To solve the problem, OAuth access tokens would need to include additional stuff. Right? They would need to indicate which client they've been given to and what identity had authorized them. If the token had those things in it, then it could be used for authentication. That's basically the idea behind OpenID Connect. So normal OAuth tokens are a black box, but ID Connect extends OAuth 2 and adds additional claims that the client can extract So these claims, well-known, the client's allowed to pull them out. And it can then, know who assigned it and who was granted to. So normal OAuth for authorization, authentication, you would use OpenID Connect. All right, so we've covered a whole bunch. Last thing I want to talk about is the Authenticator app. These are usually used in addition to one of these other techniques, and they're easier to implement than you might think. I'm sure you've seen it before, right? You log in somewhere, give them your password, they ask you for a second factor authentication, you pull the app gives you a code, type code in, get logged in. These are called time-based one-time passwords, or TOTP, and there's a standard way of implementing these things. So here's how it works. Auth authenticates to the website using whatever technique they have. The website generates a random secret key, stores it on her account. The website will typically then give her a QR code, which she can scan. And that QR code, a specially formatted URI, is associated with one of those authenticator apps. So that's how it opens. That URI tells it who issued it, the user it was for, the secret key, etc. So that's how you scan the code and it gets into your Google Authenticator. In the future, to validate the code, both the app and the server generate a code, same hashing progress, same hashing did before, using some sort of sliding time scale. That's the details of the TOTP algorithm. So there's a way they figure out what that sliding time scale would be. That's why the password kind of resets every 30 seconds or whatever. So it's the same idea as signing any other request, right? As long as both sides go up to the same value, they know that they use the same secret key to get there. The one key here is because it's time-based, your server and the client have to have the same understanding of time. If your server clock is off or something, it's not going to work for you. All right. Here's the last hour in a single slide. So link up here to the slides on my GitHub. All this stuff is there along with all of my notes. And if you have any questions, comments, or stock tips, you can get me down here. And I can do questions.
So, just go ahead. Something like SailPoint, does that fall under Authenticator apps?
That's SailPoint?
Yeah.
I don't know what SailPoint is.
It's an identity management.
So it's one of the federated identity systems. They probably do more like single sign-on, right? Where you sign in to them and that gives you access to other places.
Generally.
Yeah.
It depends upon how the, say for instance, Salesforce can potentially use SailPoint for certain clients to log into Salesforce.
Yeah, it's probably one of those, it's probably SAML in the background. If you ever used AWS Cognito, it's probably very similar. Cognito as a whole way of doing single sign-on, it's all SAML based under the hood.
In the world of encryption, right, there's evolutions, right?
Mhm. That's correct. Decrypt.
Decrypt, and is there anything on the horizon in this space?
What's coming?
It seems like this does everything, right? But even in encryption, there's always something.
Yeah,
sort of
I
on the
think
horizon.
it's probably all that signing stuff. So that those hashing functions, they're only as good as their ability to not be cracked, right? The whole thing depends on hashing being a one-way thing. So MD5 is one of the old hashing functions that's been totally cracked. So as servers get more and more powerful, you need faster and faster algorithms, or not faster, but better algorithms to make it harder to crack. So I assume that's one of the areas of ongoing evolution. I'm not really sure what else would come aside for multi-factor, right? Other ways of doing and then smarts in the back end. Probably the next maybe evolution of this would not just be, did you log in as Alice, but now that you're logged in, are you doing things that Alice would do, right? Are you logging in at weird times of the day? Did you just log in as Alice from 2 different IP addresses? So it could be smarts, and there are things that do that already. That'd be more the intrusion detection side of it than the authentication side.
And there's a cool little company over in the brewery district that does that, what you just said.
Oh, yeah?
They just changed the name of the company already. Tell you the name. Yeah, I can't remember their new name, darn it.
Cool.
Yeah, they're great.
We talked about changes, things that are coming are passkeys.
Yeah.
By different, have you looked into those to understand how they work?
I haven't, actually. I mean, I have a, you don't mean like the YubiKey, like the little, like the physical thing, but the actual pass key. I haven't looked at how Google's doing that yet.
Well, it's like iOS.
Yeah.
Introduced passkeys. Is that what it is?
I don't.
It's not the standard and then
FIDO's the
maybe,
standard for the USB keys. I remember there was this weird hardware fake that they were doing because people couldn't afford the keys. So the thought was, well, if you use a bio signature, like you have like those touch pads on your computer, well, if you program towards those, you can do a FIDO with that.
Yeah.
And now they're doing passkey. Google and Apple are doing passkey.
Yeah, I think Google just switched the pass key to the default. I haven't looked into it yet. I have 10, 10's a nice even number, 11 would be an odd number. So yeah.
It's changing too fast. We're good.
This is a great talk. It's evergreen, right? I can just keep upping this thing and it'll be current for as long as I want to do.
Start your second slide with the next 10.
Yeah.
and so the passkey, is that just longer phrasings or is there something
Well,
more?
They count it as passwordless.
Yeah.
That's the appeal.
Well, you require like
Passwordless passkeys. You require a device.
yeah.
So it's something you have versus something you know type of thing.
Right.
And at the end of the day, you're just exchanging secret key
Yeah.
is what's really.
It probably starts by having some authentication in the beginning to link it. And then once you have it linked,
What's really fun with the passkeys thing is Valve has been doing it for years with Steam.
Mhm.
They're like, oh, you want to log in, download an app on your phone, hit yes, and then you're good.
and maybe that's another new thing that, all the places where you can sign in on your phone, QR code, you sign in, trying to hook up your Roku or whatever, typing in a password through a remote is so, last year, having a QR code where you sign in on one device and then it authenticates the other device in the background. I think that happens.
Thing from my, really very superficial understanding. So passwordless is the sort of the buzzword because the ping, everybody has that. Password manager, I'm sure. So that can totally remove that piece. But let me ask the question to you, to everyone. That basically you just, when you log in, you have your, MFA means you have the password, but now you just get rid of that. As long as it has your the username and your device, whatever environment on it, then you're good. Is that what it is or not? Do you know?
That's the end goal, I think, of what they want. The downside is once you lose your phone, you lose everything. So,
Well, that's a
I'm
different
new life.
but
Yeah.
like the conspiracy theorist to me was like, oh, that's a great way to sell new smartphones. But I'm like, yeah, maybe they're not thinking that hard, or maybe they are. I don't know.
Anybody in here know how to hack MFA? Even this thing can be faked or something. That's what I'm hearing from. We have a cybersecurity.
What they're telling you, they don't want you to use SMS for MFA because the SMS, the texting thing, can be hijacked. So the TOTP, the one-time passwords, are more secure.
But
than
authenticated, Google authenticated Microsoft, that's super good.
Yeah.
Or the ISA, like some other things,
Mhm.
except using, because SMS can be easily faked. Okay,
Yes,
I
yeah.
thought that's the keyword.
There's a whole attack thing where people will, I think it's called like SMS hijacking or something, where you call in to the phone provider and you essentially take over and have that number reported to your phone. So you take someone's,
Social engineering.
Yeah.
Do SIM swapping.
yeah, SIM swap, that's what I'm thinking.
Yes,
There's also the SS7 vulnerability.
There's a fellow that I know personally here in Columbus who had potentially up to about $200,000 stolen from him via SIM swap. They eventually hunted it down to a particular T-Mobile store in Florida somewhere. Someone cloned his SIM, and he's a Bitcoin trader that's kind of like a well-known Bitcoin trader kind of guy. So they target people. And the first thing he had, the first clue he had that there was a problem was he got an email that mentioned something about his password changing. Then he started getting dozens of emails about password changes. And so they had a script, and they did it once manually, then they did every one that they could find. And then they started taking money out of his credit cards and buying URLs. Just the URL itself that should have domain names that should have some money to them. And they buy it for 20 grand and sell it for 10 grand. And that's how they launder the money and get actual money out of it. So they buy, whitehouse.com, maybe that famous one. And it should be worth, like say 80 grand, and they pay 80 grand for it and offer to sell it to somebody for 20, and then take them 20 and transfer that to some offshore account. And they do it with an automated thing until it ran out of money. Then the bank would figure out what was going on and fix it and try to relock it down. But he figured out that they had also, via the SIM thing, managed somehow or another to get some kind of monitoring, like screen scraping type monitoring into his accounts somehow. And so as they changed and fixed these things, they'd occasionally let it go for a few hours, and then they'd re-nail them and go back and redo it. And it took him about 2 weeks before they got it all unwound. And he ended up not really costing him any serious money other than buying a new phone or whatever it was. It didn't cost him $200,000, but it took him weeks to undo, and it's terrible. And that's just one guy. And that's the new thing apparently. I just sat on. I'm a member of InfoSec. So I just sat in on a new another talk about this the other day, and apparently it's mostly China, not people in China doing it, but Chinese people in the U.S. trying to get into databases more so than that is the biggest threat. The second biggest threat is people from North Korea trying to get cash. Things due to the Russia and Ukraine and cutting on a bunch of internet access points and things, and a bunch of things getting shut down and monitored better, has more or less stopped Russia from doing the cash thing. Apparently that was a thing Russia was doing. But the last one to watch out for is apparently Iran and Israel. So Iran and Israel are apparently constantly in a back and forth with one another about it. But it's all Iran attacking Israel right now. And if Iran were to suddenly decide to start attacking other economies, there'd be a much bigger problem, because it's not being very well addressed, because they're kind of practicing on Israel. So, a few months out, that's probably going to be the big one if Iran gets pissed off enough.
So the moral of the story is secure your SIMs, or else Iran attacked Israel.
Yeah, well,
It's too late for that latter.
I'll tell you how I got my SIM secured, but it is, and it is, I guess, security through obfuscation.
You can
But
call your cell provider and you can tell them to do, there's a thing they can do that makes it harder to hijack. I don't remember the
But
details.
it still happens.
Yeah.
If you go into a store,
Yeah. Mhm. Oh, yeah.
if somebody in the store is
Keep
willing,
closing.
that's what happened to Joe.
Yep.
Somebody in the store was willing to do it for,
Yeah.
$500 or $1,000, and he didn't care if he got fired. He did get fired. But, they figured out who did it and they got fired, but, what else are they going to do to him?
So the
And
apps are then more secure than the SMS.
that too.
Yeah, I'm not very trusting, because the security clearance, that the US government had in a secure database was breached by the Chinese, and they're still paying for my identity theft protection. And I have my own, because I don't trust anybody.
Nope.
Not doing it.
It's not good.
Thank you very much for your time. I appreciate it.
It's been a while.